due to the hurricane, the brush with Hurricane Dorian, hopefully this one Umberto is not going to blaze us up too badly. It's supposed to be just a tropical storm, if that. It's supposed to be coming across this weekend. So hopefully we'll have class on Monday. But concerning exam one, I have a few concepts I want to go through with you right now. So you better take notes on this. We're going to try to get on Monday as far as chapter 19.4 on equipotential lines. Here's a diagram from that chapter. And you know, we've already talked about equipotential surfaces, and they're talking about equipotential lines, but instead of thinking in 2 dimensions, but if you think in 3 and 4 dimensions, you got to talk about surfaces. So we'll be dipping into that on Monday. So I want you to study that as far as that over the weekend. Now the stuff leading up to 19.4, 19.1, 19.2, 19.3, we've talked about a lot of that stuff as well. Okay, now we're gonna try to dip at some level of depth into 19.4 on Monday, and then that will be the extent of the material for the exam. Okay, and so basically everything that we've talked about in chapter 18, which we've gone through in detail. I wish we were a little bit further along, but because of the hurricane and stuff, we're a little bit behind where we should be, but we'll be all right in the end. And up to 19.4. All right. Now, there's going to be, because I want to make it a little bit simpler exam, it's going to be mostly multiple choice, but there will be some calculations, 1 or 2 calculations, and they'll be from chapter 18. All right. I won't be giving you anything calculation wise from 19.4 for sure, because we're basically going to be just skimming into that as much as we can, but it might not be very much. So I'm not going to try to bushwhack anybody with a big fancy equipotential surface question and calculation. But chapter 18, oh yes. And what we're going to do is you're not going to be turning in written, you're going to be doing it in writing. I'll have scratch paper on the test. You'll be turning in your test, but you'll be sending in your answer to me on the iClicker, as we have done in class. Okay? And it's a little bit different on exam day because you'll be in self-paced mode. And that means you can you don't have to rely on me putting the question up on the screen, because you'll have it on the paper. And you can go to it there'll probably be 2 calculations, maybe 3, maybe 1 Cinci and 2 deluxe calculations. And you'll be able to go through each of those calculations in whatever order you feel like doing. And you can go back to them and change your answer just like you can in class. But you'll be in charge of the pace, and that's called self-paced polling, a slightly different mode. And I'll give you a set of instructions in the test printed on how to do that. Now, those of you guys that were with me last semester, you know how to do it, all right? But you can't tell your friends at your table during the test, because that would be cheating, right? But you can tell them, just look at Dr. B's instructions. It's amazing the number of times students will dive into the problems and not look at the actual instructions. And all I tell them is, oh, look at the instructions. Have you looked at that? And they go, oh, wait a minute, I missed that. So anyways. So that'll be good. Now, the nice thing about grading on the iClicker, just with a written exam problem, I can grade it for partial credit if necessary. Now, I can't always, in a class this size, normally we'll have written problems. But due to the nature of the hurricane and stuff, we're not really in a place where I want to have written problems yet that I can grade. Now, after the exam, we'll probably start having homeworks and labs, all right, and written homeworks, and those will be graded by me and by this chap over here, all right. So we'll be dividing them up, and everybody will have a few problems, just one or two graded by me, so you'll know how my grading standards are by the end of the semester for written problems. But anyways, even with iClicker, I basically get a big spreadsheet of the data from iClicker. So I can actually see the first number that you type in and then the last number. So if you type in 17 different versions of your answer, you change your mind 17 times, it will record the first answer you send and then the 17th number that you send. All right. And sometimes I can see what you're goofing up and give you partial credit. All right. Which is good because so the rest of the test will be on Scantron. So bring a raspberry colored Scantron, not the brown ones from the School of Business, the raspberry flavored ones from the rest of campus. All right, so bring one of those and a pencil, and you'll have scratch paper embedded in the test and stuff. So hopefully it'll be enough, and that'll be good. And so yeah, partial credit. So you have two scores in web courses in the grades page. One for actually you'll have three. You'll have the Scantron score, so like 47 Scantron dots, and then you'll have a separate one for 8 or however many points from clicking from the calculations, and then you'll have the third score, which will be the sum of the first two. That's the total exam one score. Now, to give you a preview, um, actually, let me look at this. This appears to be those guys taking a test the previous hour. They had a cover page to cover up everything. My cover page is basically, you put your name and your PID. Your PID is the number on your ID card, your UCF ID card, in case uh, and you'll put that on the cover page. And then there'll be I might put some of my bigger diagrams on the cover page. Sometimes I'll put a table of values or a list of, like the speed of light, coulombs, this kind of stuff that's on the board. Instead of putting it on the board, I'll put it on your cover page and you can just, see it nice and close. And so there'll be some diagrams, so I might ask you to make a calculation. I'll say, refer to the diagram on the cover page, calculate, the force, on this charge in the diagram on the cover page. And that way it doesn't have to be embedded in a small diagram. It could be a nice big one that you can work with. All right, so that'll be, and then after that'll be the multiple choice and the the calculations and stuff, true, false, that kind of jazz. So here's a cover page from a previous exam one, or part of the cover page. Diagrams, this is actually a full page for diagrams, pseudomolecule problem. Here's the full thing. And you can see I gave those students in that semester 3 different charges. And notice that in black and white, you can distinguish between positive and negative. And I'll do the same for you guys on Wednesday. All right, so you don't have to worry about the color. We don't have a color copier for exams. All right, I've been doing it on slides, but not, of course, on the exams. So I'll make them distinct. As you can see here, Q3 is a negatory, and I'll give you the nanocoulombs or whatever, and the position, A comma 0, negative A comma 0, etc., 0 comma 3A, And then the value of A, 0.42 meters. And then the field point location, H, that's at the origin. And then I ask you a question about or I ask those students a question about the electric field at point H. So you'll see something like that. Now you might not see, probably won't see this, but you might see something else similar that reminds you, oh yeah, Dr. B said there'd be something like this. Okay. Questions so far? Yes. I'm glad you asked that because that's our first clicker question. I knew secretly, I knew that you would ask that question. Do you have to memorize formulas? No, you don't have to memorize formulas. What you have to do is recognize formulas. So I'll give you a list of concepts on the left, A, B, C, D, E, and a bunch of formulas. Here's question number one. Identify this formula, and you're going to do it here in a second. In fact, I'll just start the problem. And you'll choose for number one, you'll say, okay, that's either option A, B, C. You'll bubble in A, B, C, D, or E. 10 seconds to vote. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay. Uh-oh. We got some studying to do. Uh-oh, spaghetti-o. Yeah, the correct answer is A. And for those of you that chose C, I'll just say this: read carefully. All right. Now you've got it. Now here's the thing. Number two on the list of formulas might be the Coulomb force. All right. And so you'd have, in that case, you'd have the field formula there, then the Coulomb force formula, and you have to be able to distinguish. You have to recognize which is which. All right. And so all the formulas that you will need will be in a set of formula questions. 3 or 4 matching, 4 or 5 matching, depending. So you'll see it on Wednesday. Also, I haven't decided yet how much time I'm going to give you, but I have decided this. We'll have a little mini review session clicking. We'll have a regular clicker session just to kind of review concepts on Wednesday, 15, 20 minutes, and then we'll blaze you loose with the exam. And because we got an hour and 50 minutes. So if we take 20 minutes for a little review and getting your nerves stabilized and everything, your mental equilibrium re-equilibrated, then you'll still have an hour and a half for the test. So that's not too bad. All right. Additional questions for the good of the order. Yes.
So the official subject list is from 18 all the way up to 19.4.
Official subject. And I know why you're asking me that. The official subject list is from all of 18 and up to 19.4. And Brandon, go ahead and stand up and tell them why you're asking me that.
That makes study guides
And wait a minute now. You're not dismissed from the jury box or from the witness stand. Um, where are you going to post it?
Of course, is in discussion.
Okay, in discussion. So check for it. And CJ, everybody, and in addition to being in discussions, if you catch Brandon napping, which can happen, it has happened. If you catch him napping, you'll be on my Hall of Fame. You know.
We need to get a photo.
Yeah, that's right. We have to have photographic proof. So, anyways, it's a discussion, so you can talk about anything that he's got on his list, and you know, and suggest something to add. You know, Brandon, did you forget about this? And for those of you that do, there's a very nice equation editor inside discussion, inside anywhere inside web courses. It's the little icon that has a little square root sign, and it works really nicely. And if you know LaTeX, did you learn LaTeX already? No. If you know LaTeX or Tech, that's the technical formula setting language that they use. But it's kind of WYSIWYG. You know, you can just pick and choose symbols and stuff. Works good. Um, and so if you are looking at Brandon's study guide and you want to type in a different version of a formula, go to it. You can do a lot of fancy stuff in there too. So it's really nice. Additional questions? Yes, Melanie.
Alright, so just double checking. So, concepts that you didn't cover are still coming, or everything is still coming? Because, like,
Monday we're gonna have new stuff, up to 19.4.
yeah, but like in every chapter, there's certain things that you didn't necessarily rush the students.
Yeah, you're gonna have to. So what do you not have to focus on? Is that kind of what you're asking me? Okay. Melanie's asking, what do you not have to focus on? And realistically, for me to just give you, all of chapter 18, all of 19 up to 19.4, realistically, that's not accurate. Okay, but the lectures are your key. If I talk about it in lecture, yep. But I'm not going to talk about every single paragraph in the textbook in every chapter. And for those of you that have had me in the past, you know I skip around a lot. Like I'm already talking about stuff at the end of the book, quantum mechanics, in passing. And it won't be on the test or anything, but eventually that stuff will be on the final. But yeah, you have to. So my advice to you is, yeah, chapter 18, chapter 19 up to 19.4 for the stuff that I hit in lecture. Okay, so and I try to key you in lecture the chapter and section of the textbook that we're talking about, right? But you still have to do some thinking, all right, Melanie? By the way, is anybody in here an ed major or an ed minor? No, not a single, not a single one. All right. Now, the reason I'm asking you that is you may have heard me twice in the last 5 minutes ask for any additional questions, and then I hush my mouth. I practice the 15-second rule. I learned it when I was in grad school, and it's a good rule. When you ask students for questions, always hush your big mouth for 15 seconds. And by the end of the 15 seconds, somebody will ask. Now, what is your name in the back? Isabel. Isabel did it the first time. I was in the 15 sec. Let me show you here's 15 seconds. Starting now. Done. That's 15 seconds. And usually if you use the 15-second rule, and if there are questions, they'll rise. And Melanie was the second one. So in case you're wondering if I'm just stalling and stuff, no. Well, I am stalling so that I can draw questions out of you guys. All right. Anyway, so that's the 15-second rule. Some of you may eventually become, or if you're given you become a hotshot doctor and you're over in Oslo, Norway, accepting the Nobel Prize for medicine, you know, and you're giving your speech to all those big shots in Norway, you can stop and questions and then wait 15 seconds, or any other place where you want to ask questions from the students, from your audience. All right, let's get back to field line concepts. And let me get this screen out of the way. Okay, well, we still have some more clicker. Matter of fact, we have a clicker question right now. Rain, are you here? Rain? That would be you. All right, second question. And look at Kendra in back, they're just kind of beaming. My student, she's so smart, look at her hair. See what you didn't know until now, Rain, is it's a sign of high IQ if your hair does that. That's what I've heard. So so you're doing good. 15 seconds. Yeah, we have other high IQ individuals in the room. 5, 4, 3, 2, 1, 0. Okay. Now, there's the answer spread. So we got now here, and you know what? The real answer for this one is C, because we didn't really. But I'm going to show you how to determine it now. All right. Now I'm going to give everybody that point, so don't worry about that. All right. I want to see, but you can see, that, in a situation that needs testing, this is actually great. A situation that needs testing, you have a split opinion, just like that. A distribution of ideas. In other words, so when you see that, it means, better do some more testing, or better do some more instruction, better do some more learning, which is what we are here for. Now, third iClicker question. High IQ individuals. All right, now this is Melanie. Now this one you want to answer as well as you can. If it was positively charged, see, and so the reason these iClicker questions are helpful is you might see something like this on the exam. Not this exact one. I can't put Melanie's or anybody else's photo in the exam, but I could still ask a question like this. 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. All right, now let's look at this one. Here's the spread of answers. Now notice that this spread of answers here, much more clear. And this is the correct answer. Negatively charged is correct. And so when you look at a set of information of this kind, it tells you that there's structure to it, and the structure is the correct answer. All right. Whereas the previous question, there was a little more complexity to it. All right. A little bit more randomness in the case where you don't know what the answer is. Okay. So now let me quit that. And here's the actual. So this is Joel, and yeah, we're displaying the high IQ levels here all over town here. But yeah, this is from chapter 18:8. That's the actual way it works. And I mentioned to you last time, actually, let me explain the diagram first. There's a conveyor belt, and you could hear the conveyor belt going. When we turn on the juice, that whirring sound was the conveyor belt, which you see inside profile here. There's a little brush at the top, those little spiky things on the left, B. That's a brush. That's a symbol for a brush, like a wire brush, and it just frictions up on the conveyor belt. Conveyor belt's a certain kind of a fabric, and it's connected to the metal sphere. And what happens is, uh, it's as if positive charges are being shipped off to the conductor. You know, actually, let me ask you this. Are positive charges really going into the conductor? It's negatives moving off the conductor, right? Okay, so what's happening is some positive charges are drawing the electrons out of the conductor, making the conductor net positive, right? Because it's the electrons that move. Okay, and then the electrons go out at point A into the ground. So, which makes the ground more negative. So his hair is polarized and aligns with that direction. Now, so as I mentioned, these Van de Graaff generators, the big ones, can be used as particle accelerators, and they have a little diagram over there. You see where it says ion source? So that's like a piece of radioactive, radium or something that spews out electrons or helium nuclei, positively charged particles. And then it goes through the metal sphere and accelerates as a result of it. All right. And then there's off to the lower right is a little target. Okay. So that's how they use these things as accelerators. So they don't go around, oh, let's make somebody's hair stand on it. That's nice. Let's generate some nice lightning bolts. That's nice. But what they do for research is they do this. So they juice up the ions going through that. And if raise your hand if you've ever heard of the lipid bilayer. Yeah, see, a lot of yous. Okay, things go through the lipid bilayer because of electrical interactions. They'll accelerate in one direction and not the other. That's how that works. Same thing here. Your positive ions will get accelerated outward away from that conductor. So if you want to slam them into a target of some kind, try to get some lead and turn it into gold with some alpha particles. That's how you do it. You get a source of alpha particles, which are helium nuclei, 2 protons, 2 neutrons. They get spit out of these sources like radium and stuff. Accelerate them, smash them into a sample of lead, and you'll get a little bit of gold. Problem is, it's cheaper to buy gold than to make it this way, but you can. And that's how they make exotic elements too, with particle accelerator. All the stuff above 92 on the periodic table is manufactured in accelerators like this or other kinds of accelerators. All right, so that's the Van de Graaff. Now, in general, Now, the Van de Graaff's not a point charge, it's a spherical array. But it has an electric field pretty close to what a point charge would have. So in general, and this is field line, check 18.5 figure 1, and I think actually we'll take a look at it in a minute. The electric field vectors are pointing away. So at every point on this circle on the left, if you compute the electric field vector, it's pointing radially away from a positive charge. Now the field lines would be represented as lines that connect all the way back to the charge. So the electric field vectors are arrows whose tail is at a particular position in space. The field line connects all the positions in space that are oriented in a specific direction. All right. Now for a point charge, it's particularly easy. So a positive point charge, the field lines go out kind of like porcupines. But now if you have a negative charge, it's like an anti or reverse porcupine. The field lines go inward. And remember, the field lines are oriented to the direction, Heidi, that a positive test charge would go. So if you put on any of those red lines, if you put a little teeny tiny proton down there, it's going to want to go towards it radially inward towards that negative point part, or that negative charge. Okay, so that's how that works. All right, and I'll refer, and as I said, I'm going to try to keep referring you to different chapters, sections, and even figures. This is similar to figure 2 in chapter 18.5. Now, another thing that we go over in chapter 18.5 is some other properties of field lines. Field lines are useful for a reason. They're nice to visualize certain things. They express certain concepts or measurements that you can make about your array of charges. The more coulombs of charge, the more field lines. All right. And you can think of it this way. The more we get the Van de Graaff generator to charge up that sphere, the more hair is going to stand out from somebody's head. Think of it that way. All right, more charge, more hair standing on end. Same thing here. Now, in the textbook, there's a nice little section about these properties. So let's take a look at them. This is from Properties of Field Lines, chapter 18.5. So the first one is, this is the porcupine and anti-porcupine effect. They have to begin on positive charges. They terminate on negative charges, or at infinity in the case of isolated charges. All right. So this is figure 2 from chapter 18.5. All right. That's the one that we were just talking about, the porcupines and anti-porcupine. Now, here's another part of that same figure. The number of field lines leaving a positive charge or entering a negative charge is proportional to the magnitude of the charge. Now, that's what I was just telling you. All right, the previous slide. The more charge you have, the more extra electrons you have, the more field lines that you should direct into your diagram. All right. Now, the thing is, the physical field lines are not physical, as far as we can tell. They're useful mathematical constructions like vectors. You know, a vector is not physical. It represents a physical quantity, velocity, for instance. But you don't look through the universe and see little arrows everywhere. You know, you do that on graph paper. You know, you analyze motion, you know, however, you know, using Doppler shift or whatever you're using. And then on your graph paper, in your report, in your paper, you make arrows and kind of, you know, or flow lines, streamlines, or in this case, field lines. All right. So the number, you know, and it's interesting that the guy that discovered these lines, or that first started talking about them, I guess, developed field lines, His name was Michael Faraday back in the early 1800s, first half of the 1800s. Very, very smart guy and a great guy. And he originally thought that these lines of force, as he called them, he thought they were physical. You couldn't see them, but he thought that they were physical. And we now know that they're not really physical, but they're still a very handy mathematical tool to understand that which is physical, which are the forces and stuff. Okay. Now, next one. Here's another one. Now, look at this is two charges. This is figure 8 and this is actually related to one of the problems that I like in chapter 18.5. And this one, you have a negative charge on the right and a positive charge on the left. And let's just see here. Where's my cursor? Hold on. Let me pause the cursor. All right. Now let's take a look at this. Now the field lines, they land on a bunch of field lines land on this negative one here in the gray area. All right. And a lot of them, a bunch of field lines launch from the positive. All right. So that's number one. They begin on positive, they terminate on negative. But notice the different numbers. All right. Let's start. I'm going to start counting with this one here in the southeast part of, and just give me your eyeballs for a minute. Not up here to the front, but to the screen. Let's start counting here. 1, 2, 3, 4, 5, right there, 6. Now this is the last one below the line between the two charges. 7, first one above the two charges. 8, 9, 10, 11, 12, and back to southeast. So there are 12 field lines landing on the negative charge. So write down Q equals minus 12 in your notes for figure 18.5. Right? Now let's count the positive ones. This is going to be a little trickier. All right, so I'm going to start here at this one that's going off to the left, straight west. That's number 1. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Is that right? 22? Did I count that? Is that? Did I miss one? Huh. Okay, so Q equals plus 22 or 23 for further analysis for somebody with better X-ray vision than me. All right. So that means that and notice that the field lines are much more intense over by the big charge, the big positive charge. Over here on the far end, the right end of this negative part of the array, it's kind of pokey. There's hardly anything out there. And that brings us to our next concept. The strength of the field is proportional to the closeness of the field lines, i.e. the amount per unit area perpendicular to the lines. So if you were to try to put in like a 1 centimeter square in any of these areas, and then count the field lines poking through that 1 centimeter square, up here or down here in the middle, there's a lot of field lines poking through that 1 square centimeter. All right. And so, Austin, that's where your field line or your field strength is going to be greater. All right. So the strength of the field is going to be greater. And visually, that's closer to the big charge. And it's not as close to the weak charge. right? Now over here, it's weaker. They're spread out over here. They're more sparse. And when it's so sparse that there are no field lines, electric field is zero. Right? Now, the thing about these field lines, they're, and I'm just going to give you a vocabulary word here that you've heard probably if you ever watch movies. They're all related to something called electromagnetic flux. That's right, the flux capacitor, which is how time, which was what makes time travel possible. Flux is a thing. Now the problem with that for us guys in this course is that to do flux you have to have calculus at the wazoo. So we're not going to do that. But these verbal sentences, these sentences are perfectly fine, but they all embody a flux concept or actually a law uh, involving flux of the electromagnetic field. And it's basically this last thing, the number of lines per unit area perpendicular line. You know, the flux is the amount of field lines poking through your 1 square centimeter uh, area, you know, wherever you put it. Next property, the direction of the electric field is tangent to the field line at any point. So if you look at those field lines and you want, all right, I have a point right here. So let me put my cursor right up here. Right up here at the top, you look at the field line and you can say, all right, my electric field vector there is horizontal because I'm right at the top of that curve, and it's to the right, all right, according to the arrows. So that the shape of the curve gives you horizontalness. The direction of the arrow gives you the direction of the field vector. Now, if you go um, over here on the left of the positive charge, it's horizontal all the way out, and it's leftward. Now, here's something else I want you to think of. See these two big loops? These two big, they're kind of blooping off here to the right, halfway in the middle, right down the pike. If you were to draw in the electric field right here on the symmetry line, it would be to the left, right? Because it would be aiming inward towards that negative, right? Anything out there. So you have to bear in mind symmetry, all right? Now, last thing, field lines can never cross. They're a mathematical construct, and they're oriented to a location in space. So if you have field lines crossing, you make one calculation, you get a certain shape at point A, and then you do another calculation from a different perspective and get a different direction at point A, you've made a mistake. All right. Now you're not going to have to worry about that because it's extremely difficult to map out even the only ones that are easy are the point charge field lines and parallel plates, and a few other configurations are fairly easy. But like this, the dipole field, very tough. In fact, our grad student up here would be crying for his mom if he had to. If I had to, can you do it?
On the fly.
Yeah, see, you'd have to go and crack the books and figure it out. So would I, but I've done it before. It's actually you can do it in Mathematica fairly easily. Yeah, it's kind of nice. Now, dipole fields. Let's talk about this. We talked about this upper one the other day. All right. Actually, except the one we talked about the other day was the tilted diagonal. You know, the hypotenuse of that one array that we were looking at. But see, now here's something interesting. If you look at this top one, two negative charges, so like charges, the field lines are trying to avoid this one spot here. And why is that? Because the electric field there is zero. If the field strength is zero, there's not supposed to be any field lines going through there. All right? Now also notice everything up here is pointing downward along this perpendicular bisector. And then down here, everything is upward. All right. And then over to the right, you have inward. Over to the left, you have inward, straight in. Straight in from the west, straight in from the east. Those are the symmetry lines in a dipole field. The symmetry line between the two charges, and then the perpendicular bisector of that line segment between the two charges. All right, and everything kind of curls around. And notice that this was kind of an idealized picture, as if there were no other positive charges in the universe, which there are, but this is kind of an idealization. And if there's no positive charges within a mile, you're okay. And in atomic scales, a mile is like 50 nanometers. If you're further away than 50 nanometers, you don't really, unless it's like no, even DNA. I don't think DNA is 50 nanometers long. But if you're 50, that's a mile in atomic scales, 50 nanometers for most purposes. Now this one down here, this is a dipole. This one is a dipole shaped field. This is a dipole. A dipole formally is a positive and a negative. And this one's arranged so that the symmetry axis is horizontal, and then the other symmetry axis is vertical. Now look at the symmetry axis, the vertical symmetry axis. All the field lines, you're at the very top of all the field lines. So what's the direction? Always to the right, always toward the negative part of the dipole, to that half of the paper. Now the symmetry lines, up here for the two like charges up here, you had field lines going in from the east, and you had field lines over here going in from the west. But down here in a dipole, a plus and minus dipole, you have field lines going out to the west, in from the east, on the other side over here. All right, so that's the symmetry here. It's a different symmetry, a different set of symmetry properties for the field. Now figuring out, if I gave you a point, if I gave you a point out here somewhere, and I told you the direction of the electric field, some point off the axis, you'd be able to tell me which one of those charges was positive and which was negative. Yes. I might just put that, if I could figure out some way to simultaneously burn your brains and ask this in a multiple choice question, I might just do it. That's a good question. Given the strength of a field, given the direction of the electric field vector at some point, not on a symmetry axis, just out here in space somewhere like left field, determine the location of the two charges, determine which one's positive, which one's negative. That's a nice task. Same thing down here. Now here's a famous dipole system, the water molecule. And this is a quote from chapter 18.6. In the water molecule, it's 10 electrons, 8 from the oxygen atom, 2 from the two hydrogen atoms. They tend to remain closer to the oxygen nucleus than the hydrogen nuclei. All right, so what that does is it makes the hydrogen end over here, what's that saying is, in this diagram here, the hydrogen that's basically a proton out there. And the electron that belongs to the hydrogen is somewhere in here, closer to the oxygen. And the same thing with this. So this tends to be the positive end. The hydrogen side tends to be the positive end of the molecule. And all the electrons, see the extra electrons, I don't know if you call it a valence electron, but the one electron that a hydrogen has it's going to repel the oxygen atoms, outer electrons especially, uh, away from it. And so they're going to tend to be over here on the far side of the oxygen. And so that's going to be the blue side of the molecule. Now, if you just have an oxygen atom, it's going to be purple. It's going to be fairly spherical. Same with the hydrogen, right? But if you have a molecule like this, you're going to get a and that arrow with the bar at the tail of the arrow symbolizes the dipole. Dipole is a vector. Now we're not going to calculate anything with it, but you would draw it symmetrically from the positive side towards the negative side of any molecule that you're working with. Now, DNA is extremely complex, so you have a bunch of dipole vectors to draw in if it's even possible. But for water, it's not bad. And about, let's see, 90 years ago, that's what they were calculating. Linus Pauling and all those guys were calculating the structure of hydrogen and oxygen in the water molecule and other things. And a little bit later than that, in the 50s, they were trying to figure out DNA, of course, which is much more. This is very simple structure. And I'm sure that you've talked about this in chemistry class. So hydrogen bonding, DNA is nothing without hydrogen bonding, right, between the bases. So the H's of one water molecule hydrogen bond up to the blue of another water molecule, the blue end, the negative end. And that's how they bond. That's the bonding. So hydrogen bonding. In snowflake, ice, it's the same. They get close, it cools down enough, things start moving slowly enough, they can bind together in crystals. Like snowflakes, supposedly hexagonal. If you've never seen a snowflake, I mean, if you go up north ever and it's winter, and sometimes when the conditions are right, you get gigantic snowflakes. So what you do, you can't catch it in your hand. You have to be wearing mittens or a glove. And then the surface of the glove, if it's cold enough, it'll just stay there, and you can look at it and you'll see it's six-sided. Okay, most of them. Now, another thing I want to mention to you before we finish for today, I think we're going to finish a little early today. Raise your hand if this is your last class of the week. Okay, so it's a good fraction. So now raise your hand if you're opposed to dismissing early today. What? Okay, that's a little fake out. You're trying to burn my brain. See, I know these tricks. My students getting their revenge. All right. So we're going to do a little bit. We're going to do a little bit on the document camera in a second. Shh, 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 shh. Man, I got everybody riled up on that one. Yeah, we'll try to dismiss a little early here today, but we still got a little bit more material to cover. So I'd like you to know that there's some problems that I like, and whenever I say that, here's a problem I like. Take that as a hint, a broad hint, that if you study it and then go to the midterm or final, you might be smiling a little bit more than if you hadn't studied it. And if you look at the very end of chapter 18.5, I've outlined a handful and annotated a handful of problems that I like. And so those will be good to study with if you have a study partner, or even in discussions. If you're working on any of those ones that I've denoted that I like, and you get stuck, just post something in discussions. That's your, and then I'll chip in, and then Andrew and Kendra, if they spot it, they'll chip in, and your classmates will chip in some tips. Works good. It's kind of like a virtual study group. By the way, I'm going to try to completely annotate all over the weekend, all the way up to 19 and including 19.4. So I might be alert. I might list a few more in 19 that I like. Just saying. And if I do, probably we'll go over them in lecture on Monday. Okay, in some manner, shape, or form. Yeah. What's that? No, I haven't finished. I haven't done everything I want in 18 either, but I did thoroughly review 18.5. So, but I got a little bit more in 18. And I'll make a note here to you. This last diagram about water. 18.6, I believe, is about biological systems and membranes and stuff. We'll be talking about membranes probably with chapter 19 concepts, because we're going to be talking about batteries and capacitors and stuff. And membranes, the lipid bilayer, has a lot of the same properties. So it behooves you to at least skim 18.6. I'm not going to mark that one up too much now, but eventually I may. All right, and then here's some problems here. Now, before we dismiss, I want to go over some stuff about voltage and electrostatic potential. And we're going to use the document cam. So can you, and what I'm going to do, I'm going to keep recording, and then I'll embed the PDF of the things that I am about to do on document cam in the YouTube, in the recording, which I've done in the past. All right. Yeah, do you have a marker? No, a pen. A pen should be fine. Let's see if I can adjust this. Okay, I got one. I got one. Actually, does anybody have a red pen? Do you have a red one? Or any other color than black? Krishna, could I have that chair? Yeah, thank you. This is blue? Good. Very nice. Thank you. All right. Do these adjust for height? Can you bring that all the way up? There we go. That'll help a little bit. Okay. All right. I'm going to do a few formulas here about something called electrostatic potential. And before I do that, I'll just remind you that conservation of energy in Physics 2053, total mechanical energy is equal to the kinetic energy, plus mostly we work with GPE, but sometimes also spring energy, SPE. All right. Now, if we want to extend that in 2053, we could go kinetic energy plus GPE plus spring potential energy plus electrostatic potential energy. Now, I'm going to cross out GPE from this because if you're doing electrostatic potential energy, especially if you're doing electrons and protons, gravitational potential energy doesn't make a big contribution. So this is like one Newton meter, 1 joule for a total of, and over here, the total is going to be up, like 10 to the 40 joules, meter for meter. So gravitational potential energy can be put to the side. In addition, spring potential energy is electromagnetic. Basically, at the atomic level, that's the metallic lattice being pulled apart and trying to restore its equilibrium value. And so springs oscillate for that reason. Just like the rigidity force for a table like this um, is basically electromagnetic as well. So, we could do this one here if we wanted to. However, this one's got troubles, as we mentioned, because this one, electrostatic potential energy, depending on your apparatus, can be positive or minus. So kinetic energy, no matter if your apparatus is moving, that's always positive. But this thing over here, electrostatic potential energy, is not. So what we do is we take the basic work formula. The work W is equal to F delta X for some displacement. Remember that from 2053? F delta X, and that's equal to the change in the kinetic energy, delta KE. And from that, we construct the potential energy of whatever associated with whatever that force is. So for instance, GPE is equal to minus mg delta y if you're going vertically upwards, and g is equal to negative 9.8 meters per second squared as always. So that's what we would do if we wanted gravitational potential energy. And we could do something similar to that for gravitational potential energy of the Earth. Now that's a little bit fancier, but it's very similar. Minus g m1, or m of the Earth, divided by r, right? It's an inverse r formula for the gravitational potential energy of the gravitational field of Earth. Now we can do that with the Coulomb interaction. It's kq over r for the gravitational for the electrostatic potential energy. But we're not going to do that. It would be actually, let me take that back. For the Coulomb interaction, the electrostatic potential energy would be kq1 q2 over r, right? But for and this should, I should put, we put another, here's the m of the apparatus. Okay, now it's the potential energy. Okay, and similarly, parallel thought, EPE for a point charge, KQ times the Q of your apparatus divided by the distance. All right, but that's ambiguous because of the charge plus and minus signs of the charge. So what we do is we take and redefine electrostatic potential. And we don't call it potential energy, we just call it potential. Okay, measured in volts. All right, so volts in the metric system, it's measured in volts. And the formula for it is V equals, and it's common to use the symbol capital V for the electrostatic potential, minus KQ over R for any point charge. Okay, and for us, that is going to be unique to the source charge, whatever your source charge array is. Unique at any point, as it should be, or I should say, as is helpful. And it's going to be a scalar, just like energy is a scalar. And because it's a scalar, it's sometimes easier to use this. Now you could, electrostatic potential energy up here is a scalar, but because of its ambiguity for charge, it's harder to work with. All right. Now, so what you do is you work with potentials, you do all your math, and then you figure out the potential energy, or you do all the math and then figure out the force, or the electric field, and then the force, and then from that figure out F equals ma. And inside circuits, this is the coin of the realm. The voltage in a circuit between 2 points in a circuit, just like potential energy. If there's a variation of potential energy from point A to point B, you'll have some motion. If there's a variation in the potential from point A to point B, you'll have some charge motion. Charges will move. So charges move in response to V of R. And I'll just call it V as a function of R for a point charge. All right. So, and don't forget that minus sign up here. All right. And so, so if you have a positive charge here, so there's your positive point charge. Everywhere the same radius around that point charge in a circle, actually in a sphere, that'll be at V1, some voltage V1, which is equal to minus KQ over R1. All right, I'll just even write that down, minus KQ over R1. And let me draw a bigger circle out here, a little bit further out. Well, it's kind of a circle. And so out here, V2 would be equal to minus K times the same Q over R2. All right. And so what protons like to do is protons want to flee this. All right. But electrons head in. So that's how this works. And what we're going to be talking about on Monday is electrostatic potential, which is in chapter 19. So you're dismissed. We're dismissed a little bit early. And I'll see you guys on Monday. Do some studying. And I'll photocopy this and put it into the YouTube. Actually, I think this is supposed to be a positive. Okay. This is supposed to be positive here, and here, and here. And then this will be high voltage. And this will be lower voltage. Because R2 is greater than R1. There, I like that better. Okay, let's terminate. Where's my, here we go.